Coming up on Energy Switch, we'll look at the current state and potential of nuclear fusion.
Yes, fusion and fission, they are both nuclear because they come from the nucleus. However, one is a sustained chain reaction that you're depending upon. That's fission. Whereas fusion, you have to apply that energy source in order to make it happen at all. If that goes away, it just stops.
Interesting.
In fusion, it's a real big leap forward, right? It's something where you have developed the technology for many years. I mean, we made it happen as mankind, and this is a fabulous accomplishment. So we have to create materials that withstand this type of process.
We have to make new materials.
Yep.
Next on Energy Switch, the fascinating topic of nuclear fusion.
Funding for Energy Switch was provided in part by the University of Texas at Austin, leading research in energy and the environment for a better tomorrow. What starts here changes the world.
I'm Scott Tinker, and I'm an energy scientist. I work in the field, lead research, speak around the world, write articles, and make films about energy. This show brings together leading experts on vital topics in energy and climate. They may have different perspectives, but my goal is to learn and illuminate and bring diverging views together towards solutions. Welcome to the Energy Switch. Fission is the splitting of atoms and provides the heat that drives our nuclear reactors. Fusion is the fusing together of atoms and is what powers the stars, including our sun, which means, at a high level, that fusion powers Earth, but not in any way that we can control. If we could harness fusion, it would completely transform our world, producing limitless energy, safely and without emissions, the holy grail of energy. I'll talk about the technology and its potential with Oliver Schmitz. He's a professor of nuclear engineering and associate dean for research at the University of Wisconsin-Madison, a top nuclear program, and co-founder of Rialto Fusion. Zabrina Johal is Senior Director of Strategic Development at General Atomics for their fusion projects and chairs the Communications Advisory Committee of the Nuclear Energy Institute. Next on Energy Switch, we'll discuss the potential and possibilities of nuclear fusion. The most important question I think we have to start with is it nuclear or nuclear? I mean, how do we actually say it? How do you say it?
Kernfusion.
Oh, no. You say nuclear or nuclear?
Nuclear.
Nuclear.
Definitely nuclear.
Not nuclear.
No.
Okay, we're not in Texas.
Not me.
Let's go high level to get started. Why should our viewers, our listeners care about fusion? What's the big deal?
When you think of fusion, it really is that perfect source of energy. And when you look at all the other sources that we have, they all have setbacks.
Yeah.
Look at solar and wind. They're dependent on the weather.
Well, and they come from the earth too. You got to mine all that stuff.
Correct. and you're depleting all these natural resources. Whereas fusion, a bottle of water is all one person would need for fuel in their lifetime.
That's it?
That's it. A 12-ounce bottle of water.
Like that?
Like that. So that and lithium. Whereas you look at fossil fuels such as natural gas, coal, they emit carbon, and they're also depleting natural resources.
Right.
Hydropower is dependent on geographic location. And then with fission, there's this perceived issue around safety and nuclear waste. Fusion has none of those issues.
Things to add to that, Oliver?
I think it's the clean, abundance, limitless energy source that we need. I always like to emphasize it's a baseload energy source.
Baseload being?
Being, big plants like a coal plant or like a fission plant, what we have today, so you can deploy it at scale and power the grid.
Fusion sounds like it would be some pretty hard thing to do. It almost sounds too good to be true.
Fusion is really hard.
Okay.
Well, the sun has large gravitational fields that get these nuclei close enough that they fuse. Because at the heart of it, a nucleus is positively charged. It has protons.
Right.
And as we know with magnets, like forces repel. You have to provide an energy source that gets them close enough together to overcome that barrier to cause fusion.
Okay.
And it turns out that's technologically very hard.
Okay. That's different from what we use today to make electricity from nuclear, which is a fission process, splitting. What's fission?
Yeah, for fission, it's relatively simple. You pile up uranium at the right concentration, at the right level, and burn it down. You control it with carbon rods in the simplest form. There are much more sophisticated reactors now, but that was pile number one, how it worked. And so that's, once you realize that when you have neutrons in this material permeating it, you can trigger this chain reaction and control it and burn it down.
Okay.
So that's much simpler than maintaining our plasma and convincing it to fuse.
I think most people are listening are wondering, or going to be worried about safety. If I'm scared of fission, what's going to cause me not to be scared of fusion?
I always go back to the fundamentals. Yes, they are both nuclear because they come from the nucleus. However, one's the lightest element in the periodic table and the other is the heaviest.
Right.
So they're fundamentally different. And one is a sustained chain reaction that you're depending upon. That's fission.
Fission.
Whereas fusion, you have to apply that force, that energy source, in order to make it happen at all. Mm-hmm. If that goes away, there is no danger. It's completely inherently safe. It just stops.
Yeah. Anything to add to that? Or?
Yeah, I always start with the question, why are you concerned about fission? What is your concern? You explain to people that radioactivity is all around you. It's normal. It's nothing unnormal. The few examples you have where this ended in a runaway reaction had cause to it that we know about, that we learned about, and that we can correct. But when you look at the number of deaths per terawatt hour or so from fission, this gas versus coal, you see it's a minimum amount.
Right.
I think that's a de-scaring of nuclear technology as a whole rather than fusion alone.
Okay. Well, 2 ways to do it.
2 ways.
At least. Inertial confinement fusion. Tell us about that.
So specifically, when we talk about inertial confinement, we're talking about a BB, a hollow BB, that gets filled, right? So 1 to 2 millimeters in diameter.
Okay.
That we fill it with these isotopes of hydrogen. And it's having a moment right now.
Okay.
You may have heard of the National Ignition Facility achieved ignition in December of 2022. And they actually achieved it again in July of 2023.
Okay.
And so in those experiments...
This is a historical moment as well as a BB moment.
Very historical moment,
the
yes.
BB had its moment, too.
Well, so it's still a BB.
Okay.
And what we do is we shoot this BB with a very giant laser.
Right.
They have a cylinder that surrounds the capsule, and the laser come in 2 entry holes and hits the cylinder, and it's actually X-rays that compress this capsule.
Okay.
And so when these X-rays come in and compress, it's like a balloon. You have to compress it all at the same time, 360 degrees symmetrically. When those X-rays converge on, they call it the ablator.
Right.
It has a massive force in all 360 degrees to cause the very center of it to start fusing.
Because there's nowhere else it can go.
There's nowhere else it can go.
Got it. When you say laser, it's like a bunch of them, isn't it?
It's one laser beam that gets split into 192 different beams. It stands 10 stories high and spans 3 football fields.
It's incredible.
So in December, 1 megajoule of energy went into the BB.
Okay.
And 2 megajoules, give or take, came out. So it had a 50% gain.
It's a megajoule.
A megajoule.
A megajoule. Can you relate that to something?
Oliver, help me out
megajoule. What
here.
would?
Yeah, you can compare it to the energy content in a typical candy bar that you will eat at home.
1 candy bar?
1 candy bar.
So that's what came out.
The energy equivalent of a candy bar, correct.
And later we want to have many more candy bars.
Yeah.
So here's the thing with inertial confinement fusion. Right now on NIF, we shoot 1 target a day. If we want to make this work for energy purposes, we need to shoot 10 a second.
10 BBs a second?
10 BBs a second.
Let's get to magnetic then. What goes on there?
Yeah, the plasma helps us out. The plasma is a hot ionized gas, which means that the electrons and nucleons of an atom are separated and they move separately. So therefore they can draw currents.
Okay.
And everybody probably knows when you have a current and you bring a magnet to it and move it, you can affect the current. Mm-hmm. So that's what's happening in our plasma. We use strong magnets. We form big magnetic bottles that withstand or that press against these currents in the plasma and confine it.
Okay.
By that way, they realize little pathways for the electrons and ions to stick to.
Okay.
And that's the principle of our magnetic cage.
Took a lot of energy to make the lasers. Does it take a lot of energy to make the electricity for these electromagnets?
Once you have filled the current into the superconductor, you need very little power to keep the current running.
Yeah.
Because there's no resistivity in the superconductor.
Okay.
And therefore, these are eventually magnets that practically are, feeding itself and needing very little power to be sustained.
So these are very different.
Very different.
Very different.
Pros and cons to both.
Magnetic fusion is much further along in being studied.
Okay.
Between the United States and Europe, something like $100 billion has been put into research. Wow. And now that we have these new enabling technologies, such as high-temperature superconducting magnets, such as modeling and simulation, we keep getting closer and closer to achieving new targets. And you see new goals all the time.
What are the cons of magnetic?
I mean, one critical part is how do you create and maintain the plasma in an efficient manner. We have technologies that can scale to steady-state operation, but we have them not at scale yet.
Okay.
There are other heating methods. We use neutral beams, so highly energetic neutral particles that we inject into the plasma. How do we make the laser more efficient? It's the same with the drivers for magnetic confinement fusion.
Okay. Pros of inertial confinement.
I think the accomplishment that was achieved recently, this is a first-time accomplishment, and I think it paves the way, it opens the way for more developments.
So this is a big deal, this moment.
It's a real big leap forward, right? It's something where you have developed the technology for many years, have established everything, and I mean, you made it happen as mankind, and this is a fabulous accomplishment.
Got it. What are the cons then of this
inertial
technology?
confinement?
Yeah, the inertial confinement.
I think it's going to take significant amounts of funding. And so how can you design a target that's cheap enough and continue to improve upon the lasers that won't take so much energy in order to operate to make a point where it's something commercial?
So real practical, where are we? What's the status today of inertial confinement?
We're at that point where it was like the Wright brothers moment when they first proved flight.
Wow.
Right?
So it's that significant?
It's that significant.
Okay.
We now know that this self-sustained heating is possible.
Okay.
But we need all the engineering that goes behind how to actually create a system, and that's a lot.
And that's global? We're doing it, a lot of partnerships, collaborative efforts?
There's actually a big effort in Germany, and there's a big effort in the United States.
Okay.
You see magnetic confinement as much more global from my perspective.
Okay.
It's very much a global endeavor.
How about magnetic confinement? Where are we today?
I think in magnetic confinement we are at a similar start of a new era because of technology advances. There was more than $100 billion invested into the research, and that relates specifically to the role of the magnetic field. So if you have higher magnetic field, you can build more compact systems.
Okay.
And that's the big promise now in these high-temperature superconductors.
Is it right to think that inertial confinement was kind of doing this and then had a big moment? Have there been big moments in magnetic as well that are equivalent to that? Or?
There have been equivalent big moments in the 1990s when almost simultaneously the TFTR experiment in Princeton and the Joint European Torus in Oxford showed energy amplification, so that the process produced almost as much energy as was put into the plasma.
In the 90s?
In the 90s. And then the program hovered along and explored the physics of the underlying plasma, which was great because it gives us this immense basis of knowledge that we can harvest today.
So I would argue that magnetic fusion is having a bit of a moment.
Yeah.
And that there's a lot of optimism behind it right now. Now we're almost fully constructed at the ITER project. We've done that. It's 35 nations that are coming together. Right. And so at that point, when it gets turned on and we start the operational phase, there's going to be a lot of learning that comes out of that.
Yeah.
In addition to that, we've received something like over $6 billion in private funding, venture capital funding.
Interesting.
The point you start getting private funding into something I think it accelerates the progress.
Right. Why is there business interest in fusion today?
I think the market size of what you can acquire with a technology like this is so huge and so compelling. Yeah. This would replace literally $1 trillion market.
Right.
Yeah. And these investors are smart, right? They're in it for a return. And so there will be spin-offs, there will be opportunities to perhaps develop a new type of material or a new magnet that would have other spin-off applications in other markets. I
mean, the old joke, fusion, 30 years away and always will be.
Right.
Right? Not if VC's coming in.
No.
Right. What are let me just kind of step back. Like, what would you say the top 1 or 2 challenges on the magnetic confinement side are? What are the big things?
To me, it's actually the number 1 challenge is joint, it's materials. The neutrons are energetic enough that when they go into the lattice of any material, let's say steel or some plasma-facing component, they can create helium inside of the lattice and pump it and start to make it brittle. And then the material, it doesn't degrade, it doesn't fall apart, but little flakes might go into the plasma and stop the plasma. It's not an economic process anymore. So we have to create materials that withstand this type of process.
We have to make new materials.
Yep. Yeah, we have materials that could be candidates, tungsten mixtures of some sort. This could be liquid form of metals. There's different concepts out there.
Yeah.
But the critical gap at the moment is we do not have a facility to test those before we have actually a burning plasma reactor. So we need to wait practically until one of these creates a plasma that produces fusion neutrons at scale for at least a couple of minutes. Then we can start with this.
So the process got ahead of the materials horse, so to speak, the cart.
I think that's a fair statement.
Yeah, a point on that. In fission, most of our reactors are called thermal, and the neutrons have 1 million electron volts of energy. Mm-hmm. You can do a fast reactor, which is also fission, which is 2 million electron volts. But fusion is 14 million electron volts of energy. So there are significant challenges behind the materials, as Oliver is talking about.
Right. But it also contains 14 times more energy.
Correct. Yep.
Okay. What's the top 1 or 2 challenges on the inertial confinement side?
Probably efficiency of lasers and targets, making enough targets economically.
What do we do to address that challenge?
Well, like many things, it comes down to funding. Mm-hmm. And it sort of amazes me how we can understand how fusion is almost this perfect energy source, yet we don't put a lot of money into it. And I think it's because there have been fits and starts.
Right.
The CHIPS and Science Act just authorized $1 billion for fusion funding, and for fiscal year 2024. The bills haven't come out of Congress yet, but they're somewhere under 800 already, right? 800 million. Look at China. Mm-hmm. Back in the early 2000s, China really started going into fusion full force. Several of their ministries are now working on it, and it's a fully public funded program where they're developing the workforce. And they have a Chinese fusion engineering test reactor, CFETR, that's supposed to be built and operational by 2035. And I think that's really exciting to see that happening.
Neither of you mentioned talent. Is that a problem? Do we have the talent here in the U.S.?
I mean, I think that this is one strong asset in the U.S. program. That's why I came to the U.S., that the university programs produce top quality engineers, top quality physicists. In our program, we have probably 40% international in the fusion graduate program. So that is a big attractor, but just the development growth already at the moment with the new venture firms that are on the market, they are taking all oxygen out of the room. There are no postdocs anymore. We see the shortages already now. And practically at the moment, I think the field is developing at a pace that's faster than any of the institutions can react. Some have started to react when you look into the job market for new faculty position. And at our institution, we have also done a strategic hiring initiative. And that is really the opportunity and challenge to integrate plasma with the nuclear engineering, with the material experts and so on, and create that new innovation hub also for the workforce.
I think there is a significant challenge there. Developing talent not just around the scientists and engineers, but the tradespeople, the unions, everything else that's going to take to construct it, and then we have to operate.
Yeah.
And I think the final point I'll say about this is we don't have terribly diverse talent, you know, because as you innovate, and we need innovative concepts for fusion to get it to work, you want to have many different voices around the table with many different perspectives to be as innovative as possible.
Absolutely. Let me throw it out here. How long till we actually see commercialized fusion generating electricity that will get mixed into my grid with geothermal?
So the most optimistic would be a fusion pilot plant in 2025.
Okay.
The most conservative is a fusion pilot plant in 2035. To go from a fusion pilot plant to commercial scale could be 5 to 7 years. The Chinese demonstration reactor is supposed to come online in 2035. The UK is building a demonstration reactor called STEP right now that will be coming online in 2040. ITER is supposed to commence operation initially as 2025. I think that's going to be a couple years delayed. But we're going to see some significant engineering and operation within the next 10 to 15 to 20 years.
I'm doing the math here. 2025 to 2035 for a pilot.
Early 2030s.
And then the least optimistic, 2035 plus 7, 2042 or so. Is that right? 2030 to 2042 for commercial?
For commercial.
This will be a first of its kind plant.
Yeah.
And maybe
Serial number
some
1.
of them, maybe number 1, 2, 3.
Right.
And now we aspire to have an impact on climate change and resilience.
That's just it.
Yeah.
That's just the start of it. And now you have to think, how can you roll it out on a scale that has an impact?
Right.
Yeah.
And that is again, I'm kind of trying to highlight a little bit those activities that can start now, which will seed the ground so you can really take off and accelerate when you have this first of its kind demonstration.
Right.
We are thinking about creating a fleet of several thousands of those reactors to replace the baseload capacity that we have in the US at the moment.
Yeah.
And how do we plan to do this over a minimum amount of time?
Right.
And another important thing we haven't touched upon yet is the regulatory space, which, as we know, in nuclear technology is extremely important.
The NRC, easy.
The NRC, right? The Nuclear Regulatory Commission.
Right.
NuScale, a small modular reactor right now that's being designed, has spent, I've heard 800 million, I've heard over $1 billion, in just getting NRC approval. But an important thing happened on fusion just this year. Just this year, the NRC came out with a ruling that said fusion will not be regulated like fission. They will be regulated like a particle accelerator.
Is that good news or bad news?
That is great, great news.
Yeah.
So that reduces the regulatory risk of building these and getting commercialization by a lot.
Look, I speak all over the world to all sorts of different audiences all the time. And I've always had to answer the commercial fusion question with, well, it won't be in my lifetime. Now, I can actually say, it might be in my lifetime if I take care of myself. It might be my lifetime.
Gaining momentum.
Incredible.
Yeah.
I didn't know that. I didn't know those numbers. Would somebody else sit here, push back. Would somebody else sit here and say, that's crazy. There's no way fusion goes commercial before 2042. Would anybody really push back on these dates? Because this is incredible to me.
I think people would push back on the dates if they didn't follow the science and hadn't followed the technology and understood where we are today.
Yeah.
It's a question about the debate around specific items on the critical path. If you benchmark them and validate them.
Sure.
But again, we have this portfolio of technologies that we go forward with. We will find a way. We have to find a way.
Talent and regulatory and these things are always part of anything from TR1 to TR, technical readiness level, to whatever. But I'm excited by that. You got me excited.
It is very exciting. That's very good.
Well, look, I've really enjoyed the dialogue. Zabrina, thanks for being with us. Oliver, thank you so much for this. Unlike fission, fusion is inherently safe. There are 2 main types. Inertial confinement uses a massive laser to blast a tiny hydrogen target compressing it on all sides enough to fuse. Magnetic confinement uses extremely powerful electromagnets to compress atoms in a hydrogen plasma field. Magnetic confinement is more mature, with experiments producing energy 30 years ago. This began the construction of test reactors, which should begin operating this decade. Meanwhile, inertial confinement has just had its Wright brothers moment. Experiments can now output more energy than went in. This has encouraged billions of dollars of investment in fusion, largely from China. There are many materials, talent, and cost challenges ahead, but our experts firmly believe we could see working fusion pilot reactors within 10 years, and the first commercial plants in 20. If they're right, within our lifetimes, fusion could begin to transform the way we produce and use energy. Wow.
Funding for Energy Switch was provided in part by the University of Texas at Austin, leading research in energy and the environment for a better tomorrow. What starts here changes the world.